Some have speculated that I've seen more of the natural world than anyone else. I've witnessed the natural world at its most fascinating and vibrant. But I've also witnessed startling changes that are today threatening our very civilizations. What we do in the next few years will determine the next few thousand years. On the summit of Mauna Kea, 2 miles above the Pacific, the night of May 13th, 2019, began like any other observing run. The Keck Observatory's adaptive optics, the system had locked onto the galactic center, correcting for the turbulence of Earth's atmosphere in real time, holding a steady infrared gaze on a patch of sky, 26,000 light-years away. At the instruments, Twando was monitoring Sagittarius A star, the 4 million solar mass black hole that anchors the Milky Way. For years, it had given astronomers almost nothing. A faint shimmer in the Ka infrared, a dark ember, as Drew later called it, quiet, predictable, nearly dormant. Then the detector saturated. A spike of near-infrared light surged through the system, brightening the black hole signal by a factor of 75. 75 times its normal quiescent brightness. The flare lasted roughly 2 hours, rising fast, holding, then decaying back toward baseline. In the raw data stream, it read like an instrument. Glitch, a satellite crossing the field, a cosmic ray strike on the detector array. Do check the data once, then again, then a third time. He ruled out every plausible artifact. The signal was real. The black hole that had spent decades barely flickering had just produced the brightest near-infrared flare ever, recorded from the galactic center. His words afterward became the defining description of that night. I was watching. A lion who had been asleep for 1,000 years suddenly opened one eye. The outburst did more than fill a 2-hour window in an observing log. It saturated portions of the detector, an instrument designed to study the faintest objects in the universe, was briefly overwhelmed by the very source it was built to monitor. The flare was so bright relative to Sagittarius A star's usual output that it forced a hard reset of assumptions that had governed galactic center. Astronomy for a generation. The black hole was not permanently dormant. It was capable of violence. To grasp what 75 times quiescent brightness means here, you need to understand the numbers Sagittarius A star normally operates on. The black hole contains roughly 4 million times the mass of the Sun packed into a region. Smaller than the orbit of Mercury, it should be one of the brightest objects in the galaxy. Yet it radiates so faintly that across most of the electromagnetic spectrum, it barely registers. Its X-ray and radioluminosity hovers around 10 to the 30th to 10 to the 31st ergs per second, roughly 100 billion times dimmer than a standard active galactic nucleus of comparable mass. In the near-infrared, it is even quieter. That baseline is what astronomers call quiescence. And that baseline is what the May 13th flare shattered. But this flare was not an isolated anomaly. It was the most extreme data point in a trend that had been building across 2 decades of observation. Instruments on the ground and in orbit, Swift, NuSTAR, the Keck telescopes, the gravity interferometer at the Very Large Telescope in Chile had been recording a slow, irregular increase in the frequency and amplitude of flaring from Sagittarius A. The black hole was not waking up on a single night in 2019. It had been stirring for years. The 2019 flare was simply the moment the stirring became impossible to ignore. The telescopes that captured this event represent the apex of modern observational capability, and the fact that they were all pointed in the same direction when it happened was no accident. The galactic center had become a high priority monitoring target precisely because astronomers suspected something was changing. Swift, a NASA gamma-ray burst satellite, had been accumulating X-ray snapshots of Sagittarius A star for over a decade. NuSTAR, sensitive to higher energy X-rays, had added another layer of coverage. Gravity, combining the light from 4 8-meter telescopes in Chile, had been tracking the motion of gas and stars at unprecedented resolution. And Keck, the largest optical infrared telescope on Earth, had been watching the black hole's infrared flicker for years. Together, they formed a surveillance network spanning the electromagnetic spectrum, all trained on the invisible point at the center of the galaxy. When Dew's flare triggered, the alerts went out immediately. Astronomers on other continents scrambled to point their instruments at the galactic center while the signal was still elevated. The 2-hour window became a race. Every photon captured in those 2 hours carried information about the physical conditions just outside the event horizon: temperatures, densities, magnetic field strengths, the geometry of the hot gas swirling at near-light speeds around a gravitational pit from which nothing returns. A flare like this is a probe. It illuminates the black hole's immediate environment in ways that steady-state emission never can. There is another number that sat in the background of every analysis of the 2019 flare, and it changes the meaning of the event entirely. 26,000. That is the number of light years between Earth and Sagittarius A star. The photons that saturated the Keck detector on May 13th, 2019 had left the galactic center. Around 24,000 years before the Common Era, the last ice age had not yet ended. Mammoths and saber-toothed cats walked the North American continent. Human beings were painting caves in what is now France and manufacturing stone, tools in what is now Kenya. The light from the flare was already traveling through the interstellar medium, while our ancestors built the first permanent settlements. It crossed the distance between the spiral arms of the Milky Way, while civilizations rose and fell, while the Bronze Age gave way to the Iron Age, while empires expanded and collapsed, while the telescope was invented, pointed at the sky, and refined across 4 centuries until it became sensitive enough to catch single infrared surge from the heart of the galaxy. That temporal disconnect, an event that is ancient when it reaches us, but is happening right now in the frame of the black hole, creates a strange dislocation. The flare we observed in 2019 is not a historical artifact. It is the present tense behavior of the gravitational center of our galaxy. The black hole is flaring now. The light is simply arriving now. And the question that Dew's data forced onto the table was immediate. If the black hole flared like this once, how often is it flaring now, in the present moment we cannot access? And what is it? Building toward? The shift in scientific language around Sagittarius A star after May 2019 was subtle but consequential. Before the flare, the standard descriptive frame emphasized quiescence, dormancy, quiet. The black hole was a sleeping giant, a faint radio source, a gravitational anchor that did not feed after the flare. The language began to change. Papers and conference talks started using words like variable, active, transitional. The question was no longer whether Sagittarius A star could flare, it had just done so spectacularly, but whether the flaring represented a genuine shift in the accretion state of the black hole. Had the lion merely stirred in its sleep, or was it beginning to wake? The 2-hour burst did something that years of incremental monitoring had not achieved. It shattered the illusion of permanence. The quiet was not a permanent feature of the galactic center. It was a phase, and phases end. 26,000 light years from Earth, behind a wall of dust so thick swallows nearly every photon of visible light, sits the gravitational center of the Milky Way. For most of human history, this region was a theoretical coordinate on a star chart, a point astronomers calculated but could never see. The galactic center was a hypothesis, not a place. That changed in 1974. Bruce Ballack and Robert Brown were working at the National Radio Astronomy Observatory, using radio telescopes to survey the sky at wavelengths that could penetrate the dust that optical telescopes could not. Radio astronomy was still a young field in the early 1970s, but it had already proven its power to reveal the invisible universe, pulsars, quasars, the cosmic microwave background. The two astronomers were mapping the dense star fields near the constellation Sagittarius when they detected something unusual. A compact source of radio emission, bright and unresolved, sitting at precisely the coordinates that dynamical models had predicted for the Milky Way's core. They named it Sagittarius A star. The asterisk was not chosen for drama. It originated in a convention of atomic physics and radio source catalog notation, where an asterisk denotes an excited state, an atom with an electron kicked up to a higher energy level, ready to emit a photon. The name was technical, dry, almost bureaucratic. Sagittarius A had been known as a larger radio structure in the region, This was a bright, compact component within it, and the asterisk signified that something was energetically active there. Nobody involved could have known that the label would, decades later, read like a prophecy. The object at the heart of our galaxy was not merely active, it was excited, it was waiting. But in 1974, Balick and Brown were not yet certain what they had found. What they knew was this: somewhere in the direction of Sagittarius, a powerful and compact radio source was emitting from a position that coincided with the dynamical center of the entire galaxy. The signal was faint but unmistakable, cutting through the static of deep space like a single sustained note. Balick would later describe a moment with an image that captures the strangeness of the discovery. It was like seeing a faint candle flame at the bottom of a deep well and realizing it was the heart of your galaxy. The comparison is precise. A well is a vertical shaft cut into opaque material, blocking every line of sight except the narrow opening at the top. The dust between Earth and the galactic center functions the same way. It is a barricade of gas, ice, and silicate grains, the same material that creates the glowing band of the Milky Way, visible on dark nights, concentrated in the plane of the galaxy's spiral arms. When you look up at that river of light arcing across the sky, you are seeing stars within a few thousand light years. Behind them, the dust thickens. Farther inward, it becomes a wall. The numbers that describe this extinction are not gentle. Visible light from the galactic center is reduced by a factor of 10 to the 30th power before it reaches Earth. Not 10 times, not 1,000,000 times, 10 to the 30th power. That is a 1 followed by 30 zeros. To make that number physical, consider what it would take for a single star at the galactic center to be visible to the naked human eye. Every star you have ever seen without a telescope lies within a few thousand light years of the Sunday. To see a star all the way at the core, 26,000 light years away, that star would need to be intrinsically 10 billion times brighter than our Sunday 10 billion. There are no stars that bright in the entire Milky Way. The galactic center is, in optical light, a null signal, 30 magnitudes of extinction. Astronomers quantify obscuration in magnitudes, a logarithmic scale where each 5 magnitudes corresponds to a factor of 100 in brightness reduction. 30 magnitudes means the light is attenuated by a factor of 1 trillion times, 1 trillion times 1 million. It is not that the core is faint. It is that the core is functionally not there for any optical telescope ever. This is not an instrument problem. It is a law of this galaxy. The center of the Milky Way is hidden, and for centuries that hiding was complete. Radio astronomy changed everything. Radio waves have wavelengths measured in centimeters and meters, far larger than the typical size of interstellar dust. Grains. When a radio photon encounters a grain of silicate less than a micron, across It barely notices. It passes through the dust wall that annihilates. Visible light becomes, at radio frequencies, a thin veil. Balick and Brown's detection in 1974 exploited this physics directly. They pointed their radio telescope at the predicted coordinates of the galactic center, and they heard it. The detection was not visually dramatic. No image of the galactic center emerged from that 1,974 observing run. What Balick and Brown captured was a measurement, a spike in radio flux at a specific position, recorded as a data point on a chart. The excitement was in the coordinates. The source sat at 17 hours, 40, 5 minutes and 40 seconds of right ascension minus 29 degrees of declination, the precise location that galactic rotation models had long required, for the center of mass around which the entire Milky Way turns. The discovery moved the galactic center from calculation to detection. It was no longer a deduced point. It was an observed object. You could point a telescope at, you could measure it, you could name it, and that name, Sagittarius, a star, began to accumulate weight. The asterisk that had been a dry catalogue notation slowly took on the character of a warning label. Here was something small and energetic. Here was something that should not be ignored. In the years following 1974, radio astronomers returned to the galactic center with better instruments, higher resolution, and growing conviction. The compact source Balick and Brown had found was not just a curiosity. It was persistent. It varied. It occasionally flared in small bursts of activity, barely detectable, above the background, but unmistakably there. The candle at the bottom of the well was not a steady flame. It flickered. Then came the infrared revolution. Infrared light, with wavelengths longer than visible light but shorter than radio, occupies a sweet spot in the fight against extinction. Dust grains that are opaque to blue or green light become translucent in the infrared. A telescope sensitive to infrared photons can see deeper into obscured regions than any optical instrument, though not quite as deeply as a radio telescope. Infrared astronomy allowed astronomers to penetrate the dust curtain around the galactic center for the first time and see what lived there. What they found was not emptiness. It was a dense, violent, and crowded neighborhood now called the Central Molecular Zone, a swarm of young, massive stars far hotter and heavier than the Sun, orbiting at tremendous speeds around an invisible common point. These stars were only a few million years old, mere infants in cosmic time. Yet they were already burning through their nuclear fuel at rates that would consume them in a geologic flash. And all of them, every single one, traced orbits around the same position on the sky, the same coordinates, the same point that Balick and Brown had marked with an asterisk. The stars did not just orbit a radio source, they orbited mass, gravitational mass, the kind that bends starlight, accelerates gas to hundreds of kilometers per second and holds entire clusters in its grip. Each orbit, observed over years, traced out a Keplerian ellipse that required a central mass of roughly 4 million suns, concentrated inside a volume far smaller than any star cluster could occupy without collapsing into a black hole. The stars were not circling a luminous object. They were circling the dark. The invisible point had acquired a physical presence. It had a radio voice, an infrared environment, a gravitational signature, and a growing dossier of strange behaviors. But it remained invisible in the direct sense. No telescope had ever seen it. No telescope ever would in the conventional sense. The object at the center, the black hole itself, emits nothing that can be focused into an image. Its shadow, its event horizon, its entire physical structure would remain beyond the reach of any single-dish telescope for decades more. But the discovery of 1974 had cracked open the door. A faint candle seen at the bottom of a well 30 magnitudes deep had become the most studied object in the galaxy, not because we could see it, but because we could finally hear it, feel it, and watch the stars that danced around its invisible edge. The galactic center was a place now, and Sagittarius A star was its name. Sagittarius A star is a supermassive black hole that barely earns the word active. The object sits at the gravitational center of a galaxy containing hundreds, billions of stars. Its mass, measured through the orbits of the stars that whip around it, is roughly 4 million suns. That mass is packed into a region smaller than the orbit of Mercury. The gravity at its edge, the event horizon, is strong, enough to trap light itself. The environment around it is dense with gas, dust, and young, massive stars. If you were designing a cosmic engine for maximum radiative output, you would struggle to build a better one than this. And yet, Sagittarius A star is, by the standards of supermassive black holes, almost completely dark. The numbers are not subtle. Astronomers classify Sagittarius A star as a low luminosity active galactic nucleus, a category that sounds technical until you see what it actually means. The luminosity of the black hole, its total radiative output across X-ray and radio wavelengths, hovers around 10 to the 30th to 10 to the 31st ergs per second. A typical quasar radiates at 10 to the 45th to 10 to the 47th ergs per second. Those are black holes of similar mass to Sagittarius A star, a few million to a few billion suns that are actively feeding on large reservoirs of gas. They convert the gravitational potential energy of infalling matter into radiation with brutal efficiency, heating accretion disks to millions of degrees, and launching jets that pierce intergalactic space. Their light can outshine the combined output of every star in their host galaxies by factors of hundreds or thousands. Sagittarius A star does none of this. Its luminosity is 100 billion times lower than a typical quasar of comparable mass. 100 billion. If you placed a quasar and Sagittarius A star side by side at the same distance, the quasar would be as bright as the sun, and Sagittarius A star would be a candle flame at the bottom of a very deep well. The black hole at the center of the Milky Way is not struggling to shine. It is, by every measure that matters, refusing to. Astronomers quantify how actively a black hole is feeding using a number called the Eddington ratio. The Eddington luminosity is the maximum brightness an object can achieve before the outward pressure of its own radiation overpowers the inward pull of gravity. For Sagittarius A star, with its 4 million solar masses, the Eddington luminosity is roughly 5 times 10 to the 44th ergs per second. Sagittarius A star's Eddington ratio is between 10 to the minus 8 and 10 to the minus 9. That is not a percent. That is not 1,000th of a percent. That is 1 part in 100 million to 1 part in 1 billion of the maximum possible accretion luminosity. If Sagittarius A star were a furnace, it would be running so far below capacity that you would need to press your hand directly onto. The coals to feel any heat at all. The physics behind this dimness has a name: the radiatively inefficient accretion flow, or RIAF. In a standard thin accretion disk, the kind that powers quasars and X-ray binaries, gas spirals inward in a geometrically thin, optically thick sheet. Friction between adjacent orbits heats the gas to millions of degrees, and that heat is radiated away efficiently, allowing the gas to cool, lose angular momentum, and fall deeper into the gravitational well. The process is self-sustaining and luminous. It is the cosmic equivalent of a well-tuned engine. A radiatively inefficient accretion flow is the opposite. In an RIAF, the gas is sparse, hot, and puffed up into a geometrically thick torus, more a cloud than a disk. The density is so low that particles rarely collide. Without collisions, the gas cannot cool efficiently. The thermal energy generated by gravitational compression stays locked in the gas as heat rather than being radiated away. And because hot gas exerts more pressure, it resists falling inward. Instead of spiraling down toward the event horizon, much of the material is simply ejected, blown outward in a hot wind, or advected across the event horizon while still carrying its thermal energy into the black hole. The result is a black hole that starves not because there is no food, but because the food cannot cool down enough to be swallowed. The central molecular zone surrounding Sagittarius A star is rich with gas. Molecular clouds, ionized. Streamers and the winds of young massive stars pour matter into the inner parsec at rates that, in a normal active galaxy, would trigger a luminous outburst. But the gas arriving near the event horizon is too hot, too sparse, and too magnetized to form a thin disk. It circulates, it heats further, and then it either escapes or vanishes into the dark, without ever producing the blaze of radiation that physics says is possible. There is no sustained accretion disk around Sagittarius A star. Decades of multi-wavelength monitoring radio, infrared, X-ray have searched for the characteristic signatures of a thin disk, a thermal spectrum peaking in the ultraviolet, broad, emission lines from gas orbiting at thousands of kilometers per second, the flickering variability that comes from turbulence in the inner disk. None of these have been detected at levels that would indicate a persistent thin disk structure. What exists instead is a faint, variable, and geometrically thick inflow, a riaf, that produces only occasional flares when a clump of gas or a cars. Magnetic instability briefly increases the local density. There is also no persistent relativistic jet. Many supermassive black holes, including M87, star the first black hole ever imaged, a 6.5 billion solar mass giant at the heart of the Virgo cluster, launched jets that stretch for thousands of light years, channeling energy and plasma into intergalactic space at near light speeds. Sagittarius A star, despite having a mass large enough to power such a jet, and evidence from later observations that it may spin at a significant fraction of the maximum rate, produces nothing comparable. No collimated beam, no radio lobes. No visible outflow that can be traced beyond the immediate vicinity of the event horizon. Just a faint, compact radio source, the same one Balick and Brown detected in 1974, that occasionally flickers but never ignites. For decades, this absence of activity shaped how astronomers thought about Sagittarius A star. The black hole was not just quiet, it was considered dormant, a relic of a more active past, now starved into silence. Textbooks describe the galactic center as a placid place, interesting for its stars and its gas dynamics, but not for its central engine. The Milky Way, it was said, did not have an active galactic nucleus. It had a dead one. But dormancy in a supermassive black hole is not a stable state. It is a phase. The gas reservoir that feeds the black hole fluctuates on timescales measured in centuries, millennia, and millions of years. Star formation in the central. Molecular zone produces massive stars that live fast and die in supernova. Explosions, each one dumping energy and matter into the interstellar medium. Stellar winds from the star cluster and the broader nuclear star cluster strip. Gas from aging giants and inject it into the inner parsec. Molecular clouds on eccentric orbits pass close to the black hole, are tidally stretched and leave behind streamers of gas that can take centuries or millennia to circularize and fall inward. The quiet was not a guarantee. It was an observation, a snapshot of a system that had been dim for the few decades humans had been watching. But a few decades is nothing. The black hole has existed for billions of years. Human astronomy has existed for centuries. Our entire monitoring campaign spans less than 1/10,000,000th of the black hole's lifetime. To conclude that Sagittarius A star was permanently dormant based on that thin slice of data was not just premature, it was arrogant. The puzzle hung over galactic astronomy for 30 years. A 4 million solar mass black hole sitting at the bottom of the deepest gravitational well in the galaxy, surrounded by gas and stars and dust, with all the ingredients for a luminous accretion flow, and yet radiating at 100 billion times below its potential. The RIAF model explained the mechanism of the dimness, but not the percent cause. Why was the gas so sparse? Why did it not cool and collapse into a thin disk? Was some process actively preventing the accumulation of a denser gas reservoir? Or had the black hole simply not been fed a large meal in recent cosmic history? And beneath those questions lay a more unsettling one. If the quiet was temporary, if the black hole was merely waiting, cycling through a naturally low phase in a longer pattern of activity, then what would happen when it woke back up? 4 million suns, 100 billion times too faint. No disk, no jet, no sustained feeding. A hole in the sky. That is what they were looking at. For 30 years after Ballick and Brown's radio detection, the galactic center remained a source, not an object. A compact emission region, extraordinarily massive, according to indirect arguments, but still fundamentally a radio blip on a catalogue page. No telescope could resolve it. No instrument could separate the black hole's signature from the swarm of stars around it. The dust that hid the center from optical view also blurred the view at longer wavelengths, smearing the faint radio and infrared signals into an unresolvable haze. To prove that Sagittarius A star was a black hole, astronomers needed to see something orbiting it. Not gas, not diffuse clouds. A single star tracked year after year, tracing an orbit so tight and so fast that no other explanation was possible. The star would need to pass close enough to the central mass that its motion would reveal the gravitational field in fine detail, and the measurements would need to be precise enough to distinguish a single point of mass from a diffuse cluster of dark objects that might mimic a black hole's pull. The technical challenge was immense. The galactic center is crowded. Within the central parsec, hundreds of thousands of stars pack into a volume that, in our own stellar neighborhood, would contain only a few dozen. Separating one star from another at a distance of 26,000 light-years requires resolving power, far beyond what conventional ground-based telescopes could achieve. Atmospheric turbulence blurs starlight into quivering blobs. The stars at the galactic center were not just faint. They were smeared together, their individual motions lost in a wash of overlapping light. Two groups took on the problem. Andrea Ghez at UCLA led a team using the Keck Observatory in Hawaii. Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics led a competing team using the Very Large Telescope in Chile. Between them, they deployed a technology that had only recently become practical for astronomy: adaptive optics. The principle is straightforward, but the engineering is brutal. A deformable mirror, thinner than a contact lens and backed by hundreds of tiny actuators, changes shape 1,000 times per second. It compensates for the turbulence in Earth's atmosphere in real time, straightening out the distorted wavefronts of incoming light. The result is an image that approaches the theoretical diffraction limit of the telescope, as sharp as if the atmosphere did not exist. With adaptive optics, the Keck telescopes and the VLT could resolve individual stars in the central cluster. The two teams began monitoring campaigns in the mid-1990s, taking images of the same patch of sky night after night, year after year. They identified dozens of stars close to the radio position of Sagittarius A star and started measuring their positions. A handful of stars were much closer to the center, and they were moving fast. The star designated S2, also called S0-2 by Gez's group, became the prize. Its orbit brought it closer to the central mass than any other known star. At closest approach, called pericenter S, 2 passes within roughly 120 astronomical units of Sagittarius A star. That is about 3 times the average distance between the Sun and Pluto. In gravitational terms, it is a knife-edge pass. The teams tracked S2 through multiple positions along its orbit. They watched it accelerate as it plunged toward the center. In 2002, it reached pericenter, slingshotting around the invisible point at a speed of 5,000 kilometers per second, 18 million kilometers per hour. That is nearly 2% of the speed of light. A star, a sphere of fusing plasma hundreds of thousands of kilometers across, traveling at a velocity that would cross the continental United States in less than a second. Let the weight of the measurement settle. 5,000 kilometers per second. The fastest spacecraft ever built by humans, the Parker Solar Probe, reaches speeds of about 190 kilometers per second at its closest approach to the Sonde S. 2 moves 25 times faster than our fastest machine. A bullet fired from a rifle travels at roughly 1 kilometer per second. S2 moves 5,000 times faster. The motion is not a drift, it is a whip crack. Gez and Genzel each applied Kepler's laws to S2's orbit. Kepler's third law relates the orbital period and the semi-major axis of an orbit to the mass of the central object. For S2, the orbital period is just over 16 years. The semi-major axis, the average distance from the black hole, is about 970 astronomical units. Plug those numbers in, and the mass of the central object comes out with brutal clarity. 4.1 million suns. Both teams arrived at numbers that agreed within a few percent. 4.1 to 4.3 million solar masses concentrated within a region smaller than 100 astronomical units across. The concentration argument is what made the case airtight. 100 astronomical units is about 3 times the size of Neptune's orbit. Inside that volume, 4 million solar masses of material are packed. If that mass were made of anything other than a supermassive black hole, a cluster of neutron stars, a dense swarm of stellar mass black holes, some exotic configuration of dark matter, the system would be unstable. That many objects jammed into so small a space would collide, merge and collapse into a single black hole on a timescale far shorter than the age of the galaxy. The only stable configuration was a single, enormous black hole. The measurements did more than prove the black hole's existence. They proved that. It was the dominant gravitational object in the galactic center. S2's orbit is a clean Keplerian ellipse with the black hole at one focus. There is no detectable perturbation from any other massive object in the inner region. The black hole rules alone, its gravity swamping everything else within the central light week. Ghez later described the experience of watching the stellar motions in a phrase that captures the disorientation of seeing physics at this scale. She said, "When you see those stars whipping around, you realize you are not in Kansas anymore. The center of the galaxy is a violent, beautiful physics laboratory." Violent, beautiful. A laboratory. Each word earns its place. The violence is in. The speeds, the gravitational stresses that would tear apart any object less tightly bound than a star. The beauty is in the simplicity of the orbit's pure. Ellipses, tracing out the geometry of space-time around a point mass. And the laboratory is real. The galactic center is a place where Einstein's general relativity can be tested in a regime that no solar system experiment can reach. S2's orbit allowed the first tests. General relativity predicts that light leaving a strong gravitational field is redshifted, its wavelength stretched as it climbs out of the gravitational well. As S2 approached pericenter in 2018, both teams measured the redshift in the star's spectral lines. The shift matched the relativistic prediction to within a few percent. In 2020, the Nobel Prize in Physics was awarded to Andrea Ghez and Reinhard. Genzel sharing the prize with Roger Penrose, whose theoretical work had established that black holes are a generic prediction of general relativity. The citation recognized the transformation of Sagittarius A star from a hypothesized object into an empirically verified supermassive black hole. A third of the prize went to the observers who had spent decades pointing telescopes at the center of the galaxy, refining their adaptive optics and building an unassailable case from thousands of individual astrometric measurements. The work did not stop with S2. The monitoring campaigns have now identified dozens of stars in the central arc second, each tracing an independent orbit around the Passon black hole, a star designated S4000. 714 was found to reach a speed of 24,000 kilometers per second at pericenter, 8% of the speed of light, making it the fastest known star in the galaxy. the transformation is complete. Sagittarius A star was a radio source. Then it was a candidate. Now it is a measured object. Its mass, 4.1 million suns. Its size, smaller than 100 astronomical units. Its gravitational field, strong enough to accelerate a star to a significant fraction of light speed. The ghost at the center of the galaxy has a weight. It has a location. It has a ledger of stars that orbit it. Their positions recorded night after night for a quarter of a century. The monster had been weighed. The next question was whether it was truly asleep, and if not, what it would take to wake it. In 2011, Stefan Gillessen was sifting through data from the Very Large Telescope when he noticed something that should not have been there. A faint smudge of infrared emission moving on a trajectory that pointed directly at the galactic center, not orbiting, not drifting, falling. Gillessen and his colleagues at the Max Planck Institute for Extraterrestrial Physics tracked the object across multiple nights, refining its orbit with each new data point. What emerged was a trajectory so extreme that it forced every astronomer who saw it to sit forward in their chair. The object, designated G2, was on a highly elliptical path that would bring it within 36 light hours of Sagittarius A star. Not light years, not light weeks, light hours at closest approach. G2 would pass roughly 150 astronomical units from the event horizon, a distance smaller than the orbit of S2, smaller than any known object had ever approached and survived. The timing was precise. Periapsis, the point of closest approach, would occur in early 2014. Astronomers had 3 years to prepare. The nature of G2 made the encounter even more tantalizing. Initial observations showed it was not a star. Stars are point sources, compact and unchanging in G2 was extended, smeared across several milliarc seconds, and its spectrum showed emission lines from hydrogen gas. It appeared to be a cloud of gas and dust, a few Earth masses in total, stretched into a long stream by tidal forces as it accelerated toward the black hole. A gas cloud falling into a supermassive black hole is the raw material for a feeding event. The expectation was simple. The cloud would be torn apart, heated to millions of degrees, and partially swallowed, producing a flare of radiation that could outshine everything else at the galactic center. The astronomical community mobilized. Every available telescope that could observe the galactic center was aimed at Sagittarius A star, the Very Large Telescope. Keck, the Swift X-ray Telescope, NuSTAR, the Chandra X-ray Observatory, each instrument was tasked with monitoring a different wavelength band, building a multi-wavelength picture of what everyone assumed would be the most dramatic feeding event ever observed in our galaxy. Gillessen later described the mood among the scientists as electric. People were calling it the cosmic popcorn. Everyone was waiting for the show to start. The cloud crossed the inner boundary of the known stellar orbits in mid 2013, it was now moving at thousands of kilometers per second, stretched into a filament by the differential gravity, the side closest to the black hole pulling ahead of the far side. Tidal forces were beginning to shred it. Every model predicted that the shredded material would form a temporary accretion stream, spiraling inward, heating through friction and compression, and finally releasing a burst of radiation as it crossed the event horizon. Some models suggested the flare could be bright enough to pierce the dust that normally obscures the galactic center. The uncertainty only heightened the anticipation. Pericenter arrived in March and April of 2014. Telescopes around the world recorded the moment. Data streamed in from Chile, Hawaii, and space-based observatories. The astronomers waited for the flare. Nothing happened. Not literally nothing. The X-ray and radio emission from Sagittarius A star did increase, but by a factor of 2 or 3, not the 100-fold or 1,000-fold, brightening that many models had predicted. The infrared emission barely flickered. The cloud, or whatever G2, was passed through its closest approach and continued on its orbit, battered and stretched, but fundamentally intact. It had not been torn to pieces. It had not been swallowed. It had given the black hole a glancing blow and kept moving. Gillison summed up the collective anticlimax in one word: the black hole. Basically just burped. The burp was quiet. Measurable, but quiet. For months afterward, the X-ray and radio flux remained slightly elevated above quiescence, then settled back toward its pre-encounter levels. The monster had been offered a meal, and it had barely nibbled. The failure of G2 to produce a major flare forced a thorough rethinking of what the object actually was. A pure gas cloud, unbound by any internal gravity, should have been shredded by the tidal forces long before reaching pericenter. The fact that G2 survived suggested it had a dense, compact core, something with enough self-gravity to hold itself together against the black hole's pull. The most plausible interpretation, advanced by several groups in the aftermath of the encounter, was that G2 is not a simple gas cloud at all. It is a low-mass star enshrouded in a thick envelope of dust and gas, a type of object now classified as a G-object. G-objects are one of the more puzzling discoveries at the galactic center. The handful of them have been identified in the central parsec, all showing the same curious hybrid nature. Compact cores that behave like stars, surrounded by extended dusty envelopes that look like clouds. G1, discovered earlier, shares this dual nature. G2 is now considered the second confirmed member of the G object. Population and its survival through pericenter supports the interpretation that these are not transient gas clouds, but long-lived objects, perhaps binary stars, that merged, their outer layers puffed into a dusty veil by the collision. This reinterpretation reveals something essential about Sagittarius A star's personality. The black hole is picky about its food. It does not simply swallow whatever comes near. A star, even a small one wrapped in dust, can hold itself together and pass through the danger zone with only superficial damage. The black hole's gravitational reach is vast, but its effective feeding cross-section is tiny. It cannot grab what it cannot break. The weak response to G2 was the first clear sign that Sagittarius A star was not completely asleep. A truly dormant black hole, one with zero accretion and zero interaction with its surroundings, would show no change at all when a massive object passed close. The burp, however faint, proves that the black hole is capable of reacting. The feeding mechanism works. It simply requires very specific conditions, material that is diffuse enough to be torn apart, close enough to be captured and oriented in a way that allows angular momentum to be shed efficiently. The encounter established a baseline for interpreting all subsequent flaring activity. Before 2014, the infrequent flares from Sagittarius A star were unexplained events with no clear trigger. After G2, astronomers had a template, and an object passes close, some fraction of its material is stripped away, the stripped gas spirals inward, and a brief flare results. The G2 burp was small because the stripped mass was small. Future encounters with more diffuse objects could produce much larger flares. The telescopes did not turn away after the burp. The monitoring campaigns built up for G2 were maintained. And as the years passed, the astronomers who kept their eyes on the center began to notice something. The quiet was not as quiet as it used to be. The faint flares that had always been part of Sagittarius A star's behavior growing more frequent, slightly brighter, slightly longer. The trend was subtle. No single flare was dramatic enough to cause alarm. But in the cumulative record, year stacked on year, the black hole was getting livelier. The cosmic popcorn had not popped in 2014, but the oil in the pan was beginning to shimmer. 5 years after the burp, on a Monday night in May 2019, Tuan Do was alone on the Philae summit of Mauna Kea. He was not expecting anything unusual. He had drawn the night shift at the Keck Observatory, tasked with monitoring the galactic center in the near-infrared. The black hole, as always, was supposed to be quiet. Then the ember exploded. In less than a minute, the brightness of the black hole surged by a factor of 75. The detector, calibrated for a quiescent source, saturated pixels. In the core of the image went white, overwhelmed by photons that had traveled 26,000 years to hit that exact piece of silicon at that exact moment. Du stared at the screen. He checked the data, checked it again, checked it a third time. He ruled out satellites crossing the field of view. He ruled out cosmic ray strikes on the detector. He ruled out instrumental artifacts, thermal noise, calibration errors, every possible mundane explanation that an observer trained in skepticism reaches for when the data says something impossible. The flare was real. It lasted roughly 2 hours. 2 hours in which the black hole at the center of the Milky Way blazed brighter than it had ever been seen. Not by a small margin, but by a factor that made every previous flare look like background noise. The nearest comparable event was a flare in 2012 that had brightened by a factor of 20, and that was considered extreme. This was nearly 4 times brighter. The 75-fold surge meant the black hole was pouring out more near-infrared energy in those 2 hours than it normally emits in weeks. Tu had been studying the galactic center for years. He knew the black hole's moods, its rhythms of quiet, punctuated by small flares. This was not normal. He reached for a metaphor that captured the shift. It was like watching a lion who had been asleep for 1,000 years suddenly open one eye. The image is precise. The lion did not roar. It did not stand. It opened one eye. The black hole had not ignited an accretion disk. It had not launched a jet. It had simply stopped being asleep for 2 hours, and in those 2 hours it had looked at us with an intensity that no one had ever recorded before. The flare saturated portions of the detector. Astronomers hate saturation. A saturated pixel is a pixel that has received more photons than it can count, which means you lose precise photometry for the brightest part of the image. The fact that Sagittarius A star saturated a professional infrared detector built to observe faint stars means it was genuinely, shockingly bright. The quietest monster in the known universe had become, for a brief window, the brightest object in the galactic center. The flare was not an isolated anomaly. By the night of the 13th of May 2019, a long-term trend had been building for 2 decades, and the flare was the most extreme point, on a curve that had been bending upward. The evidence had been accumulating in data from multiple instruments. SWIFT had been monitoring the galactic center since its launch in 2004. NuSTAR joined Watch in 2012. Keck's infrared cameras had been taking data for even longer. The gravity instrument at the Very Large Telescope Interferometer, which combines 4 telescopes to achieve resolution equivalent to a single mirror hundreds of meters across, began operations in 2016 and added the ability to track flares with astrometric precision, pinpointing exactly where the emission was coming from, relative to the black hole's position. All of these instruments told versions of the same story. The flaring rate was going up. Not monotonically, there were quiet months and active months, quiet years and active years. But the long-term trend, extracted statistically from thousands of individual observations, showed that the average brightness of Sagittarius A star in both X-ray and near-infrared had been creeping upward since the late 1990s. The flares were not just more frequent, they were brighter. The baseline, quiescent level was also rising, though more slowly and less dramatically. The 2019 flare sat at the extreme end of this distribution. a 2-hour burst, 75 times quiescence, saturating detectors, visible in multiple wavelength bands. It was, by any statistical measure, an outlier, and outliers in astrophysical data are either errors or messages had eliminated the error. The immediate question, asked in observatory common rooms and on email chains and in hastily arranged telecons, was simple and unanswerable. What caused it? The research community fractured along familiar fault lines. One camp pointed to G2. The close passage had occurred in 2014, and the black hole's weak response at the time had been a disappointment. But what if a response was not instantaneous? What if the stripped material from G2's dusty envelope, torn free during the close passage, had taken 5 years to spiral inward through the accretion flow, finally reaching the inner edge in 2019 and dumping its energy in a concentrated burst? The timescales were not impossible. Accretion is not a free-fall process. Gas spirals in through a disk, losing angular momentum through viscosity and magnetic turbulence, and the infall time can be years or decades, depending on the radius where the material was initially deposited. Another camp disagreed. The physics of the accretion flow around Sagittarius A. Star, they argued, is inherently stochastic. The gas that feeds the flares comes not from a single source like G2, but from the general reservoir of hot, sparse plasma that fills the central parsec, blown off the surfaces of massive stars by their own radiation, stirred by stellar winds, funneled inward by magnetic fields. In this picture, the black hole's feeding is a random process, and the long-term trend is just a statistical fluctuation. A 75-fold flare is rare, but rare events happen in random distributions. The apparent increase in flaring rate could be an artifact of more sensitive instruments and more dedicated observing time. A third camp took the middle ground. The G2 passage, they suggested, had not directly fed the flare, but had perturbed the system. The passage of a massive object through the inner accretion flow could have triggered instabilities, disrupted magnetic field configurations, sent shocks through the ambient plasma that took years to propagate inward. The 2019 flare was not the direct result of swallowing G2's envelope, but a delayed consequence of the gravitational disturbance G2 created. The data could not adjudicate the dispute in 2019. It still cannot not definitively. The flare was both a data point and a Rorschach test. What you saw in it depended on what you already believed about the black hole's nature. What the flare did, regardless of its cause, was shatter the illusion of permanence. Before the 13th of May 2019, it was possible to think of Sagittarius A star as a static object, a gravitational anchor, fixed and unchanging, exerting its pull on the galaxy with the same quiet steadiness year after year, century after century. The flare erased that assumption. The anchor is not fixed, it moves, it varies. It can, without warning, and for reasons we do not fully understand, brighten by a factor of 75 in less than a minute. The quiet is not a permanent condition. It is a phase, and phases end. The flare had shown that the black hole was not static. 3 years later, a different kind of image proved that it was not invisible either. On the 12th of May 2022, a collaboration of more than 300 scientists released, something no human had ever seen. The first direct image of Sagittarius A star, the heart of the Milky Way, 26,000 light-years distant, rendered not as a mathematical abstraction, but as a glowing ring of radio light surrounding a perfect darkness. The instrument that captured it is called the Event Horizon Telescope. It is not a single dish, but a planet-scale array of 8 radio observatories, from Hawaii to Chile to the South Pole, synchronized to within trillionths of a second by atomic clocks. Working together, they achieve a resolution equivalent to a telescope, the size of Earth itself. Enough to read a newspaper headline in New York from a street cafe in Berlin. Enough, in principle, to see a black hole. The principle was proven in 2019, when the same collaboration released the first ever image of a supermassive black hole, the monster at the center of the galaxy, M87, 55 million light-years away, with a mass of 6.5 billion suns. That image showed a bright, asymmetric ring surrounding a dark central shadow. It was a triumph, but it was a portrait of a stranger. M87 star is not our black hole. Sagittarius A star is ours. And it is far harder to photograph. The difficulty begins with scale. On the sky, the shadow of Sagittarius A star spans approximately 52 micro-arcseconds. An arcsecond is 1/36. Hundredth of a degree. A micro-arcsecond is 1/1,000,000th of that. 52. Micro-arcseconds is the apparent size of a tennis ball on the moon, as seen from Earth. But the real challenge was not the size. It was the speed. M87 star is massive and ponderous. The gas spiraling around it takes days or weeks to complete an orbit. Sagittarius A star, despite packing 4 million solar masses, is a sprinter. Gas at the innermost stable orbit whips around the black hole in just 4 to 30 minutes. Over the course of a single night, the source changes completely. You are not photographing a mountain. You are photographing a hummingbird's wings. The imaging teams had to invent algorithms that could freeze time. They divided the data into short segments, reconstructed images from each, and then searched for a common structure that persisted across the frames. Multiple independent groups worked the same data in parallel, using different methods, different assumptions, different codes. None of them knew what the others were finding. Only when all the pipelines converged on the same ring of light, would the collaboration trust the result? Katie Booman was one of the scientists who wrote those algorithms. The night the final image came through, she was not expecting it. The processing had been running for weeks, and the email arrived late. She opened it. On her screen was a glowing donut. The ring was bright and uneven, brighter on one side, exactly what the theory of relativistic beaming predicts when billion-degree plasma rotates at near light speeds. If the material is moving toward the observer on one side, its light is Doppler boosted. If it is moving away, the light dims. The asymmetry traces the direction of spin. Booman saw that immediately, but her eye did not linger on the spin. Bright rim. It went to the center. The image was there, she said later. It looked like a glowing donut. That dark spot in the middle is what everything in our galaxy orbits. We were looking at the shadow of eternity. The dark spot is not the event horizon itself. The event horizon is smaller a sphere, only about 12 million kilometers across, the boundary from which nothing can climb. What the image shows is larger: the photon sphere, the radius at which light itself can orbit the black hole before falling in or escaping. Any photon that passes closer than this radius is swallowed. The result is a shadow, cast by the black hole's gravitational lens onto the sky. That shadow is what the Event Horizon Telescope resolved a dark circle some 50 micro-arc seconds across, precisely the size that general relativity predicts for a 4 million solar mass object at the galactic center. The image proved the black hole exists. The flare proved it could stir, but proving that the stirring represents a genuine change and not merely better eyes. Watching the same old silence, that is a different problem entirely. A single bright night proves nothing. The universe is full of transient events, random flares, statistical outliers that catch the eye precisely because they are rare. To claim that Sagittarius A star is changing its behavior over years or decades, you need more than one dramatic data point. You need a trend. The search for that trend began long before Tuan Do saw his detector saturate in 2019. For more than 2 decades, a network of space-based and ground-based instruments has been staring at the galactic center with a patience that borders on obsession. Swift has been monitoring Sagittarius A star continuously whenever the galactic center is visible, accumulating thousands of hours of exposure. NuSTAR, with its harder X-ray vision, joined the watch in 2012. Gravity began operations in 2016. And Keck's infrared cameras have been gathering data on the same field for more than 15 years. What this armada has recorded is not subtle. Over 2 decades, the number of detectable flares per year has climbed. The average near-infrared brightness of the black hole, measured during its supposedly quiet state, has crept upward, not by factors of 100, but by factors of 2 or 3, a signal that would be invisible on any single night but unmistakable when you stack thousands of nights together. On the face of it, the data are shouting that something has changed. The black hole is brighter and more active now than it was in 2005. But here is where the ground begins to shift. There is a counter-argument. It comes from the same community, using the same data, applying the same statistical tools. And it says, in substance, be careful. You are comparing apples to oranges. The telescopes watching Sagittarius A star today are not the same telescopes that watched it 20 years ago. Swift did not launch until 2004. New Star arrived in 2012. Gravity saw first light in 2016. The Keck instruments have been upgraded multiple times, their detectors replaced with more sensitive arrays. The total observing time devoted to the galactic center has increased massively. In the 1990s, a handful of astronomers pointed infrared cameras at Sagittarius A star for a few nights per year, and they were lucky if they caught a flare. Today, the black hole is monitored on a near continuous basis. Imagine you have been listening to a forest for 20 years. In the first decade, you visited once a month for an hour using your unaided ears. In the second decade, you installed a network of directional microphones, amplified the signal, and started recording 24 hours a day. You would hear more bird calls, more rustling, more sounds of life. But does that mean the forest has become more active? Or have you simply gotten better at listening? This is the observational bias problem in its purest form. The apparent increase in flaring activity could be entirely explained by the fact that we are looking more often with more sensitive instruments and catching events that would have been missed in earlier decades. When you correct for the increased observing time and improved sensitivity, the underlying flaring rate may have been roughly constant. The black hole is not waking up. We are simply paying better attention. The counter-counter argument is equally technical and equally defensible. It acknowledges the observational bias, but insists that the increase persists even after correction. When you normalize by observing time, when you account for detector sensitivity, when you apply strict flare definition criteria that are consistent across all epochs, the trend remains statistically significant. The baseline brightness has risen by a factor that exceeds what instrumental drift alone can explain. One analysis, published in 2023, examined 14 years of Keck infrared data and concluded that the mean flux from Sagittarius A star increased by roughly 50% over that period, and that the probability of this occurring by random chance was less than 1%. Another group, looking at overlapping X-ray data from Swift and New Star, found that the rate of bright X-ray flares doubled between 2012 and 2022, after correcting for exposure time. The opposing group counters that the flare definition criteria used in those studies are themselves flawed. What counts as a flare? A doubling of flux above baseline? A tripling? A 5 sigma excursion above the local mean? Different. Definitions produce different catalogues, and changing the threshold by a small amount can make a marginally significant trend disappear entirely. The baseline itself is poorly defined. There is no truly quiet state for Sagittarius A star. Only a continuously flickering background of low-level variability. Where you draw the line between flare and non-flare is an arbitrary choice, and the trend you find depends on where you place that cut. This is not a dispute between experts and amateurs. It is a dispute between experts and experts waged in the pages of the Astrophysical Journal at conferences, in the grey literature of preprints. Both sides have access to the same data. Both sides use rigorous statistical methods. Both sides publish in peer-reviewed journals, and they reach opposite conclusions. The core of the disagreement is a problem that has haunted astronomy since Galileo first pointed a telescope at the sky. How do you extract a genuine astrophysical signal from an imperfect, inhomogeneous, human-collected dataset? The instruments change. The people operating them change. The weather changes. The calibration drifts. The funding priorities shift. You are not measuring a controlled laboratory experiment. You are measuring a wild source across decades with tools that are themselves evolving. For Sagittarius A star, the stakes of this dispute could not be higher. The entire awakening narrative rests on a statistical knife edge. If the trend is real, then we are witnessing a phase transition in the nearest supermassive black hole, a rare opportunity to study accretion physics in real time. If the trend is an artifact, then we have been fooled by our own improving vision, mistaking better data for a changing universe. At present, neither side has delivered a knockout blow. The statistical significance of the flaring increase hovers in that uncomfortable zone where it is. Too strong to ignore, but too weak to be definitive. More data will resolve the question eventually. But eventually, in this context, means another decade or two of monitoring. Enough to double the baseline and see whether the curve continues to rise or plateaus at a new level. One fact, however, stands apart from the statistical trench warfare: the May 2019 flare. Even the most aggressive correction for observational bias cannot explain away a single event that saturated a detector built to study a supposedly quiescent black hole. That flare, regardless of what else is happening, is a real astrophysical outlier, the brightest near-infrared outburst from Sagittarius A star. In the entire history of infrared astronomy, it tells us that quiescence is not a steady state. It is a word we used because we had not yet seen the exceptions. Now we have. And whether the black hole is waking or merely stretching in its sleep, the quiet monster we once imagined no longer exists. Most supermassive black holes announce themselves by firing beams of matter and radiation across their galaxies. M87 star shoots a jet of plasma 5000 light years into intergalactic space, a thin, magnetized column of electrons and positrons moving at nearly the speed of light, glowing in X-rays and radio from one end to the other. Its power source is the spin of the black hole itself. Thread the event horizon with a strong, ordered magnetic field. Couple those field lines to a rotating black hole, and you have what physicists call the Blandford-Znarek mechanism, an electromagnetic dynamo that converts the rotational energy of space-time into a collimated outflow. This is how the brightest quasars in the Pors universe outshine their host galaxies. The jet is the signature of a machine running at full torque. Sagittarius A star is spinning. The Event Horizon Telescope image released in 2022 showed a ring of radio emission around a dark central shadow, and that ring was not uniform. It had a bright crescent, the classic signature of Doppler boosted. Light from a black hole in which material is swept along by the frame dragging of curved space-time. The asymmetry is consistent with moderate to high spin. The measurements carry large uncertainties and depend on model assumptions, but the implication is clear. The black hole at the center of the Milky Way has angular momentum. It has the fuel, in principle, to power a jet. Yet, Sagittarius A star has no persistent jet. Not a faint one, not a small one, not one visible in any wavelength across decades of multi-frequency monitoring. The same object that produced the first direct image of a black hole shadow in our own galaxy refuses to produce the outflow that appears nearly universal among comparably massive black holes. That silence is not a minor discrepancy. It strikes at the foundation of how we understand black hole energy extraction. The failure mode connects directly to the accretion environment. A jet requires a large-scale ordered magnetic field dragged inward by infalling matter, concentrating near the horizon into the coherent funnel geometry that the Blandford-Znarek process requires. Sagittarius A star has none of that. No sustained disk. The accretion flow is hot, sparse, geometrically thick, and magnetically disordered on small scales. The field lines that thread the event horizon are tangled, their directions randomized by turbulence in the surrounding plasma. Even if the spin is high, the electromagnetic coupling to the external medium is weak. There is nothing to collimate. A second failure mode operates alongside the field geometry. A jet requires particles. In a dense accretion environment, that plasma is plentiful. At Sagittarius A star's accretion rate, the particle density near the horizon is so low that even an efficient electromagnetic coupling cannot load enough material onto the field lines to produce a visible, sustained outflow. The engine may be running, but the exhaust is invisible. This forces a harder question. If spin alone is not sufficient to produce a jet, then our understanding of jet launching is incomplete. The standard picture spin plus magnetic field equals jet has served astrophysics well for M87 star and for the quasars that illuminate the early universe. But it fails here. It fails at the one object in the universe where we have the best view of the event horizon, the most precise measurements of the surrounding environment, and the longest baseline of monitoring data. That failure is not a defeat. It is a constraint. It tells us that whatever the necessary and sufficient conditions are for launching a relativistic jet, they are more specific than current theory acknowledges. The magnetic field geometry must meet a threshold. The plasma loading must exceed a minimum. The accretion structure must provide a specific kind of collimating environment. There is a forward edge to this puzzle that connects directly to the awakening if the flaring trend is genuine. If the accretion rate is slowly rising, then the conditions at the galactic center are changing. A sustained increase in the infall rate would begin to build a denser, more organized accretion structure. The power magnetic field, dragged inward by more material, would become less disordered. The plasma density near the horizon would rise. At some threshold, the conditions for jet launching could be met. Sagittarius A star could turn on a jet where none exists today. A jet propagating outward from the galactic center would drive a shock into the surrounding gas, ionize the molecular clouds within its path, heat the medium, and inject cosmic rays into the galactic halo. The giant gamma ray, lobes that extend 25,000 light years above and below the galactic plane, are thought to be relics of exactly this kind of event. A new jet would begin writing a new chapter in that archive. We are not there. The current activity is far too feeble to launch a detectable outflow. But the absence of a jet today is not evidence of permanent suppression. It is evidence of present conditions. And present conditions, as the 2019 flare demonstrated, can change in less than a minute. If you could stand a few light hours from Sagittarius A star, you would look up and see something that should not exist. Stars, dozens of them, young, massive, blazing blue-white stars, no more than a few million years old, packed into the innermost parsec of the galaxy. They swing around the black hole at distances as small as a few hundred astronomical units. The most famous, S2, plunges to within 17 light hours of the event horizon on its 16-year orbit. Yet S2 belongs to a whole population. The star cluster, whose members number in the dozens, with more being discovered each year. They are among the most luminous stars in the galaxy, spectral types O and B, still burning hydrogen on the main sequence. They are cosmic infants perched on the lip of a 4 million sun, gravitational well. That is the first paradox. The second is that standard astrophysics says they cannot be there at all. Star formation requires a dense, cold cloud of gas to collapse under its own gravity. But the tidal forces near Sagittarius A star are savage. Inside about 1/10 of a parsec, the black hole's gravity would pull the near side of any cloud much harder than the far side, stretching it into a thin strand and tearing it apart long before it could ignite nuclear fusion. The region where the stars now orbit is a tidal shredding zone. You cannot simply take a standard molecular cloud and expect it to birth a star there. It would be ripped to atoms. So how did these young stars get so close? The question has tormented theorists for 2 decades. 3 main ideas compete, and each carries a distinct flavour of impossibility. The first proposal is that the stars formed right where we see them, in a special transient environment. A massive self-gravitating disk of gas may have once encircled the black hole dense enough that its own gravity overwhelmed the tidal forces locally, allowing instabilities to trigger the collapse of gas clumps. This in situ formation model gets the job done on paper, but it demands very specific initial conditions. An unusually cool, massive disk, perhaps fed by an infalling giant molecular cloud that lasted just long enough to spawn dozens of stars before being consumed or dispersed. Numerical simulations struggle to reproduce the right stellar masses and orbital distributions without fine-tuning. The second idea is migration. The stars may have been born farther out, beyond the tidal danger zone, and then spiraled inward over millions of years. Dynamical friction, the gravitational drag that a massive object feels as it plows through a field of smaller stars or gas, can shrink an orbit. The Kozai lead-off mechanism in which a distant companion star perturbs an orbit into a high eccentricity plunge can also deliver stars deep into the center. The problem here is timescale. The stars are young. Migration must be fast enough to bring them in before they evolved off the main sequence. The third scenario abandons the notion of a quiet birth entirely. In the extreme, crowding of the galactic center, stars can collide. 2 lower mass stars slamming together at hundreds of kilometers per second can merge into a single, more massive star that shines bright and looks deceptively young. A whole population of stars could be built from the wreckage of an older stellar cluster. This merger model sidesteps the star formation paradox altogether. But it too carries a tension. The collision rate required to produce the observed number of massive stars is uncomfortably high. None of these theories fully satisfy the observations. Each leaves a gap between the simulation and the telescope image. The stars sit at the intersection of gravity, plasma physics, and stellar dynamics, where our best models fray at the edges. And then there is the deeper thread that ties the paradox to the black hole itself. The stars are only a few million years old. That means something happened in the galactic center a few million years ago, something that either compressed gas until it ignited, or drove stars inward, or shattered an existing cluster. The timing aligns with another clue. The giant Fermi bubbles are thought to be relics of a violent outburst from Sagittarius A star between 2 and 6 million years ago. During that episode, the black hole may have shone millions of times brighter than it does today. A flare of that magnitude would have flooded the central molecular zone with radiation, cosmic rays, and shock waves. Those shocks could have compressed gas clouds, triggering the burst of star formation that gave birth to the stars. The stars may be the children of a black hole that briefly roared. Carry that logic forward, and the current awakening gains a new dimension. If a spike in activity millions of years ago could birth a generation of stars, what might a renewed uptick do? Could a new generation be forming right now, hidden in the infrared glow of the central parsec? The conditions are not identical to today's. Flaring is far weaker than the Fermi bubble outburst, but the process is non-linear. A small increase in pressure can trip a cloud past its stability threshold. There are already dense gas clumps within a fraction of a parsec of Sagittarius A star that are teetering on the edge of collapse. A sustained decade of elevated X-ray flux could be the push that turns one of them into a protostar. The stars already whisper that the galactic center is not a one-way gate to annihilation. It is an environment of terrible fertility. The most violent place in the galaxy is also the one where stars, against all odds, insist on being born. Above the plane of the Milky Way, something is boiling. It does not belong to any star, any cluster, any known object we can point to and name. It extends for 25,000 light years into the northern galactic halo and another 25,000 light years below. Two gargantuan lobes of gamma-ray light, symmetric, diffuse, and hot. They glow at energies of 1 billion electron volts and higher. They're called the Fermi bubbles, and they are the afterglow of a violence that predates human existence by orders of magnitude. The Fermi Gamma-Ray Space Telescope discovered them in 2010. The science team was combing through the all-sky map when they found an excess that would not go away. A pair of enormous bubbles, sharply defined at their edges, centered on the galactic nucleus. They stretched from the constellation Virgo through the southern sky and erupted again in the north, tracing a colossal hourglass with Sagittarius, A star at its waist. The bubbles are so large that the solar system sits only about halfway out inside one of them. We are inside the past outburst of our own central black hole. The photons that trace these structures are not thermal. Their spectrum reveals. They arise from energetic cosmic ray electrons and protons slamming into ambient magnetic fields and low-energy light, boosting them to gamma-ray energies through inverse Compton scattering. The bubbles are a particle accelerator run amok, a reservoir of high-energy plasma that has been expanding outward for millions of years, pushing into the circumgalactic medium and carving out a cavity that the telescope now records. The energy budget is staggering. To inflate bubbles of this size and brightness requires roughly 10 to the 55th ergs, the equivalent of converting more than 10,000 solar masses entirely into kinetic and radiative output. That is not a starburst. That is a central engine firing at full throat. The timing points directly at Sagittarius A star. The leading model simulates a bipolar jet or disk wind launched from the black hole during a single energetic episode. The bubbles' age, modelled from their size and estimated expansion speed, lands between 2 and 6 million years ago, exactly the window that coincides with the star paradox. The black hole that today operates at 100 billion times below its theoretical maximum was, for a brief geological moment, a true quasar-level monster. It blazed, it carved, and then it stopped. The fuel ran out, the disk dissipated. The black hole went quiet and left behind these two echoing towers of radiation, cooling slowly, marking the site where the galaxy's heart last seized with full fury. But the Fermi bubbles are not the only gamma-ray signal that has confounded astronomers. Nestled within them, surrounding the galactic center itself, is a more compact, more enigmatic glow. It is spherical, it is steady, and it has resisted explanation. Since 2009, Fermi's Large Area Telescope has detected a spherical excess of GeV, gamma rays centered precisely on Sagittarius A star. It extends outward for a few thousand light years in all directions, softer in spectrum than the bubbles, but far more intense than the diffuse gamma ray background. The signal does not flicker. It does not align with known gas clouds or point sources. It simply emanates from the center in a smooth, symmetric bloom. Two explanations have fought for dominance in the literature, and neither has won. The first is a detection of dark matter. If dark matter consists of weakly interacting massive particles with masses in the range of 30 to 50 billion electron volts, those particles should occasionally collide and annihilate with each other, producing a cascade that ends in gamma rays with a characteristic energy spectrum. The density of dark matter is highest at the center of the galaxy, forming what theorists call a dark matter spike, a steep cusp, gravitationally focused by the supermassive black hole. When you model that spike and calculate the annihilation rate, the predicted gamma-ray flux and spatial distribution match the observed excess with haunting precision. The implication is enormous. Sagittarius A star may be embedded in a halo of invisible mass that is literally destroying itself one particle pair at a time. The second explanation is more mundane but equally profound. Millisecond pulsars, neutron stars, the compressed cores of dead massive stars that spin hundreds of times per second. Their rotating magnetic fields accelerate particles that produce gamma radiation in a beam that sweeps across the sky. Individually, they are faint, but thousands of them, packed into the galactic bulge, could collectively produce a diffuse glow that mimics the dark matter signal. The pulsar hypothesis gained momentum when researchers found a similar excess in the Andromeda galaxy. Also centered, also spherical, also consistent with either dark matter or a population of unresolved rotating neutron stars. The controversy remains unresolved, with major reviews published on both sides. If the excess is dark matter related, Skir A star would be embedded in a dark matter, a spike that could influence its dynamics and accretion history. If pulsars, the environment would contain an unexpectedly high population of neutron stars, a concentration shaped by the same unknown process that birthed the young massive. Either way, the galactic center is far stranger and more active than we thought even a decade ago. Both possibilities connect directly to the Fermi bubbles. The same outburst that inflated those giant lobes would have injected energy, shock waves, and magnetic fields into the surrounding medium. A shock front ploughing through the central molecular zone could have temporarily boosted the dark matter annihilation rate and left a remnant glow. Or it could have triggered a burst of star formation that rapidly produced a generation of massive stars which evolved quickly and left behind millisecond pulsars as their corpses. The sphere of excess gamma rays may be the ashes of the same fire that carved the bubbles. This is a lattice of linked evidence. The young stars, the giant gamma ray, lobes, the spherical central excess, the past flare activity, all point to a galactic nucleus that cycles between quiescence and eruption on million-year timescales. The current awakening is the weak, ongoing aftershock of that cycle. Every flare, every surge in X-ray flux, every shock front that ripples outward from the central parsec injects a small amount of fresh energy, fresh cosmic rays, fresh magnetic turbulence into the halo. Observatories now watch for this. The HAWEC Gamma Ray Observatory in Mexico, the HESS Telescope Array in Namibia, and Fermi itself continue to monitor the galactic center for any drift, any edge, brightening, any sign that the bubbles are not purely ancient but actively responding to the stirring below. The Milky Way's center is not a fossilized museum of a single past explosion. It is a system in feedback, a black hole embedded in dark matter and gas and stars, all exchanging energy across scales from the event horizon to the circumgalactic medium. We happen to be alive during a relatively quiet interlude, but the architecture of the bubbles tells you that quietness is temporary. The next major outburst could be 1 million years away, or sooner. The physics does not specify an exact repeat interval, only that the conditions to produce an energetic flare can recur, and that when they do, they leave signatures visible for millions of years. Afterward, the lion has roared before. The bubbles are the echo, and the faint spherical glow around the black hole, whether it speaks of dark matter or spinning stellar corpses, is the proof that the quiet is never absolute. Right now, a photon you cannot see is entering your eye. It was born in a storm of magnetized plasma circling a 4 million solar mass black hole at the center of the Milky Way. And it has been traveling toward you for 26,000 years. When that photon left Sagittarius A star, the Earth was something else entirely. The great ice sheets that buried North America and Europe were in full retreat. Mammoths still walked Siberia. Somewhere in what is now France, a human being pressed a hand to a cave wall and blew pigment across their fingers, leaving a silhouette that would outlast every empire. Homo sapiens had only just begun to paint its inner world onto stone. And at that exact moment, a flare erupted at the galactic center. Its light crossed the void while the last ice age ended, while agriculture was invented, while cities rose and fell, while human beings built telescopes and pointed them at the sky and wondered what they were. 26 millennia. That is the gap between the event and the observation. Every image you have seen of Sagittarius A star, the radio shadow from the event horizon. Telescope, the infrared flare captured by Keck, the X-ray flickers recorded by New Star is not a live feed. It is a delay, a fossil. The black hole we watch today is the black hole of 26,000 years ago. Whatever it is doing right, now, at this second, we will not know for another 260 centuries. This is not a metaphor. This is the speed of light, the absolute limit of information transfer in the universe. And 26,000 light years is close by cosmic standards. It is practically next door. Yet it severs us completely from the present tense of the galactic center. Now let that number breathe. The entire recorded history of the human species, from the first cuneiform tablets pressed in Sumer to this moment, spans roughly 5,000 years. The light from Sagittarius A star that reaches us tonight began its journey 5 times further back than the invention of writing. When that photon departed, no human being on Earth had ever built a city. The wheel was 17,000 years in the future. And the black hole does not operate on human timescales. Its flaring patterns, the decades-long brightening, the century-long quiet phases, the million-year dormancies between true outbursts unfold on a rhythm that makes a mockery of our calendars. The species Homo sapiens has existed for perhaps 300,000 years. That is 0.3 of 1 million years, a rounding error in the life of a black hole that has been cycling for over 10 billion. Our entire evolutionary history is a single exhalation. Recorded civilization is shorter still. If the black hole's billion-year existence were compressed into a 24-hour day, the entirety of human history, every war, every symphony, every cathedral, every equation scratched on a blackboard, would occupy the final 0.03 of a second, a flicker, a glint, and Sagittarius A star would not notice. It cannot notice. It is a gravitational singularity, not a consciousness. But the asymmetry cuts in one direction only. We can notice it. Andrea Ghez, who tracked the stars and proved the black hole was real, once called the awakening a geological event in the life of our galaxy. Not a threat, not a promise, a geological event. She was reaching for a category that does not exist in normal language, because the thing she was describing does not exist in normal time. An earthquake lasts seconds. A volcano erupts for months. A mountain range erodes over tens of millions of years. And this black hole contains all of those timescales simultaneously. Its flares are earthquakes in space-time, rising and falling in hours. Its accretion cycles span centuries. Its outbursts reshape the galaxy over millions of years. And we happen to be alive during a moment when the instrument sensitivity and the black hole's flickering have intersected. We can see. The weight of that should not produce fear. It should produce a strange, difficult vertigo. The anchor of the Milky Way is a living, changing system, and we have emerged during a phase we can finally watch. But the vertigo is real, and it comes from realizing that the object does not belong to our timeline at all. Carl Sagan understood this. He said it plainly, without flinching. The universe is alive within us. So when I look up at night, I never feel small, I feel large. I feel as large as the universe itself. He was not being sentimental. He was making a physical claim. The iron in your blood, the calcium in your bones, the oxygen you just inhaled, every atom, heavier than hydrogen, was forged in the core of Those stars lived and died in the Milky Way. They orbited the galactic center. They were part of the same gravitational system that now stirs 26,000 light years from where you sit. Andrea Ghez echoed that same truth sharply. Every atom in your body except hydrogen was forged in a star, and that star was likely orbiting our galaxy's supermassive black hole at some point. We are literally connected to this monster. Its gravity holds us in place. The connection is not poetic, it is literal. The material that makes up your body. Once circled Sagittarius A star. It was swept into the accretion flow, heated to millions of degrees, mixed with other stellar debris, blown outward in a supernova, shockwave, and eventually incorporated into a new generation of stars, planets, life. You are not a spectator watching a distant object through a telescope. You are a piece of the system that has become conscious of itself. The black hole's awakening is not happening to something else. It is happening in the galaxy that made you. This is the perspective that the 26,000-year delay forces upon us. The light is ancient when it arrives. The object is ancient when the light departed. But the material connection is immediate. The atoms are here now. The gravity is here now. The galaxy is here now. and the black hole, whatever version of it exists in the present tense, we cannot access, continues to hold the entire spiral in its grip, whether we watch or not. The flaring we detect is not a warning, it is a postcard from the Pleistocene. The awakening we debate is a statistical argument over a trend that may have started before the fall of Rome. And the shadow we imaged in 2022, that glowing donut of billion-degree plasma, is the gravitational footprint of an object that has been quietly, relentlessly shaping the Milky Way for 10 billion years. We are the first generation to see it directly, the first to measure its mass precisely, the first to watch it stir. But we are not the first to be held by it. Every ancestor, every mammoth, every trilobite that ever lived on this planet was anchored by the same invisible mass. The difference is only that now we know. So when you hear the phrase 26,000 light years, do not translate it into miles. Do not try to visualize the distance. Translate it into time. 26,000 years of silence. 26,000 years of travel through dust and magnetic fields and the thinning remnants of ancient supernovae. And then arrival. A photon that left the galactic center when mammoths walked hits Detector at the Keck Observatory in 2019, and a scientist named Tuan Do stares at his screen in disbelief. That is the gap. That is the connection. That is what it means to be alive during a geological event in the life of the galaxy. The black hole does not know we are watching. It cannot, but we know. And the knowledge changes nothing about the physics and everything about the story. The flare that Tuan Do saw in 2019 was not just a bright flash on a detector. It was energy leaving the black hole and entering the galaxy. And once energy leaves, it does not vanish. It heats gas. It strips electrons from atoms. It pushes on dust and reshapes the chemistry of everything within reach. A single 2-hour flare is a small thing in the vastness of the central molecular zone, but sustained flaring, year after year, decade after decade, accumulates, and the accumulation changes the environment. The central molecular zone is not empty. It is a reservoir, roughly 60 million solar masses of gas, mostly molecular hydrogen, laced with carbon monoxide, ammonia, and complex organic molecules swirl within a few hundred parsecs of the Cassix galactic center. This gas is dense by interstellar standards, 100 to 1,000 particles per cubic centimeter. It is cold, often just 10 to 20 degrees above absolute zero. It is turbulent, stirred by supernova explosions, magnetic fields, and the gravitational tides of the bar. And it is the raw material from which stars are made. When Sagittarius A star flares, it emits hard X-rays and ultraviolet photons. These photons do not travel far through dense gas before colliding with an atom. The collision does one of two things. It can heat the gas, directly kinetic energy, transferred from photon to particle, raising the temperature, or it can ionize the atom, knocking an electron free and changing the chemical state of the cloud. Ionized gas behaves differently from neutral gas. It couples to magnetic fields. It radiates more efficiently. It resists gravitational collapse. Star formation requires cold, dense gas that has radiated away its thermal energy and succumbed to its own gravity. Heat the gas, and it expands. Ionize it, and magnetic pressure stiffens it further. Raise the temperature across a wide enough volume, and the threshold for gravitational collapse shifts. The mass required to overcome thermal pressure, the gene's mass increases. Clouds that might have formed stars remain diffuse. The reservoir sits idle, too warm to condense, too ionized to fragment. This is one path. Photoevaporation. The black hole's radiation boils gas away from the surface of dense clumps, stripping the raw material before it can collapse. Sustained over thousands of years, this process can truncate star formation in the company's estate, in a parsec. But there is a second path, and it runs in the opposite direction. If the radiation flux arrives in bursts unevenly across the cloud, it does not merely heat. It compresses. A shock wave from a high-energy flare slams into a molecular cloud. The outer layers ionize and begin streaming away, but the reaction drives a pressure wave deeper into the cold interior. That wave can squeeze the gas beyond the threshold for collapse. The same energy that evaporates the periphery can trigger star birth in the core. This is not speculation. It has happened before, and the evidence is still in. Orbit around the black hole. The young stars are only a few million years old. Their very presence is a fossil record of a previous active phase. The explanation is that a self-gravitating disk of gas formed around the black hole. During a period of higher accretion, perhaps 2 to 6 million years ago, the same epoch that produced the Fermi bubbles. The energy that fed the disk came from the black hole itself, a quasar-level outburst that dumped enough radiation into the surrounding gas to reshape its structure entirely. The black hole destroyed and created in the same gesture. The young stars we see today are the children of that violence. The current awakening is far weaker than that ancient outburst. The flaring we measure is 100 billion times dimmer than a true quasar. But the principle is the same. Energy leaves the black hole. It enters the gas reservoir, and the alteration can push the system in either direction, sterilization or fertilization, depending on the timing, the intensity, and the geometry of the clouds. We are watching this feedback loop in real time. No other supermassive black hole in the universe is close enough, quiet enough, and well instrumented enough to permit this kind of observation. The Milky Way is a calibration point. The physics we extract here, the relationship between X-ray flux and ionization fraction, the threshold for shock-triggered collapse, the coupling between magnetic fields and partially ionized gas scales to every galaxy in the cosmos. The numbers are local, The laws are universal. The loop does not stop at the inner parsec. The energy that photoevaporates gas or compresses clouds propagates outward. Heated gas rises out of the galactic plane. It carries with it the magnetic fields that were anchored in the molecular clouds. It carries cosmic rays, high-energy particles accelerated in the shock fronts, the flares themselves. Over thousands of years, this hot, magnetized plasma rises, above and below the disk, feeding the diffuse halo that surrounds the Milky Way. If the current flaring persists, if the decades-long brightening is genuine and continues, it will contribute fresh energy to that outflow, not enough to inflate. New bubbles. The current activity is far too weak for that, but enough to be detectable. X-ray telescopes like eROSITA are already mapping the hot gas within the bubbles. The Cherenkov telescope array, now under construction, will measure the cosmic ray population with unprecedented precision, a sustained flare cycle. Would imprint itself on those observations, a specific spectral signature, a particular distribution of particle energies, a subtle asymmetry in the magnetic field geometry that points back to the central engine. The black hole would no longer be studied only through its immediate environment. The orbiting stars, the infalling gas, the shadow ring at 5 Schwarzschild radii. It would be studied through its galaxy-scale effects, the halo as a detector, the bubbles as an archive. This is what it means to witness a geological event in the life of a galaxy. The timescale outstrips a human life. The consequences will not fully manifest for millions of years. The stars that form or fail to form in the central molecular zone because of today's flaring will not reach the main sequence until the Earth has been reshaped by plate tectonics beyond recognition. The cosmic rays that are accelerated now will spiral through the halo for hundreds of millennia before they strike a detector we have not yet built. Yet the measurement is happening. The data is accumulating. The photons are arriving. Every flare is a data point in a curve that will take centuries to complete. We have traced the story from a faint radio whisper in 1974 to a shadow ring captured in 2022. From stars whipping around an invisible point to a gas cloud that refused to be swallowed. From a flare that saturated a detector and forced an astronomer to check his data 3 times, to the slow realization that the quietest monster in the known universe is not quiet anymore. The Event Horizon Telescope image is not a simulation. It is not an artist's rendering. It is a measurement. Photons that traveled 26,000 years, captured by 8 observatories synchronized across the entire planet, combined by algorithms that took years to write and months to run. The result was a ring, a glowing donut, slightly asymmetric, 52 micro-arc seconds across. Inside the ring, darkness. That darkness has a name. It is the shadow of the event horizon, the boundary where gravity becomes absolute. And that shadow is not an absence of light. It is a Prediction made visible. General relativity said the shadow must be there. It said the ring must be roughly 5 Schwarzschild radii across. It said the asymmetry must encode the spin of the black hole and the direction of its rotation. Every one of those predictions held. Baumann received the email late at night. She opened the attachment. She stared at the screen. The ring was there. She later said the words that will echo through the rest of this century. We were looking at the shadow of eternity. She was not being poetic. She was being precise. The shadow is what everything in the Milky Way orbits. Every star, every planet, every grain of dust. The sun, traveling at 800,000 kilometers per hour around the galactic center, traces a circle that points to that dark spot. The Earth, pulled along by the sun, traces a circle that points to that dark spot. You, reading or hearing, these words are moving around that dark spot right now. And it is no longer a mathematical abstraction. It is a place. We can point to it. We can measure its diameter. We can watch it change. That last word matters. Change. The EHT image is not a static photograph. Sagittarius A star is variable on timescales of minutes. The gas swirling at the innermost stable circular orbit completes a circuit in roughly 4 to 30 minutes, depending on the radius. Hotspots flare and fade. Magnetic field lines snap and reconnect. The ring itself wobbles, brightens on one side, dims on the other. The image we saw in 2022 was a time average, a freeze frame of a system in violent motion. Future EHT observations will not show the same ring. They will show a ring that has evolved. A ring that is, in the most literal sense, alive. The black hole is not a monument. It is a weather system. And we have just begun to watch the weather. Gez knew this before the image existed. She spent 25 years tracking stars that no one else could see, measuring positions with a precision equivalent to standing in Los Angeles and watching a soccer ball in New York. She watched S2 reach perihelion, whip around the invisible point at 5,000 kilometers per, and she understood, long before the shadow was imaged, that the black hole was not separate from us. She said it plainly. Every atom in your body, except hydrogen, was forged in a star. And that star was likely orbiting our galaxy's supermassive black hole at some point. We are literally connected to this monster. That sentence is not metaphor. It is nucleosynthesis. The carbon in your proteins, the oxygen in your blood, the iron in your hemoglobin, the calcium in your bones. All of it was manufactured in the cores of massive stars. Stars that formed in the central molecular zone. Stars that spent their brief, brilliant lives orbiting within a few light years of Sagittarius A star. Stars that died in supernova. Explosions. scattering their enriched material across the galactic disk. That material cooled, condensed, and eventually became the sun and the planets and you. The black hole's gravity held the system together. Its cycles of activity and quiescence determined when those stars could form, how long they lived, and where their remains would be deposited. The connection is not spiritual, it is mechanical, it is chemical, it is gravitational, it is real. And now the anchor is stirring. The quietest monster, the black hole that astronomers dismissed for decades as permanently dormant, has revealed itself as dynamic and unpredictable. The 2019 flare was the most extreme event yet recorded, but it will not be the last. The long-term monitoring continues. SWIFT still points its X-ray telescope at the Spore galactic center every day. NuSTAR still measures the hard X-ray spectrum of every flare. Gravity still tracks the infrared flickering with milliarc-second precision. Keck still watches the stars trace their endless ellipses. The next generation of instruments is already arriving. The extremely large telescope, with its 39-meter mirror, will see the galactic center with resolution 10 times better than anything before it. The Cherenkov telescope array will measure the gamma-ray halo with sensitivity that makes current instruments look blind. The next EHT campaign will add more telescopes, higher frequencies, and the ability to make movies instead of snapshots. If the flaring trend is genuine, if the black hole is not just fluctuating but genuinely increasing its accretion rate, these instruments will catch the transition. They will measure the emergence of a jet or confirm its continued absence. They will watch the central molecular zone respond. The Milky Way will become the most closely observed black hole laboratory in the universe. And if the trend is not genuine, if the apparent awakening is an artifact of better coverage, then the monitoring will still be worth it. Because even a black hole that fluctuates stochastically without any long-term trend is a black hole we do not fully understand. Every flare, every quiet period, every wobble of the ring adds a point to the curve. The curve will eventually speak. The shadow we have seen is the orbit of everything we know. That orbit is not a circle drawn on a static page. It is a path around a living engine, an engine that breathes, an engine that has been quiet for longer than the human species has existed and is now, within our lifetime, within our instruments, beginning to beat louder. We are not outside observers. We are inside the system. The gas that surrounds Sagittarius A star is the same gas that made the Sunday. The energy that flares from its inner accretion flow is the same energy that once triggered the birth of the stars whose deaths made us possible. The black hole is not a threat. It is not a promise. It is not a symbol. It is a piece of the machine that built the galaxy. And the machine is not finished. It is still running. It is still shaping the environment. It is still creating and destroying, compressing and evaporating, heating and cooling. The timescales are too long for us to see the full cycle. A. Human life is a single frame in a film that has been running for 13 billion years. But we are the first generation to see even one frame clearly. The first to know what the shadow means. The first to watch the heart beat. The awakening of Sagittarius A star is a geological event in the life of the Milky Way. It will not finish in our lifetime. It will not finish in 1,000 lifetimes. But the event has begun. The data is arriving. The shadow is visible. The anchor is no longer still. We are living inside the first chapter of a story that will take millions of years to tell. And we are the first to read it.